Today we are going to look at 2D stress transformations, which essentially is converting stresses from one coordinate system to another. And we are going to look at 2D stresses in this case, and later on in the class we'll look at 3D stress transformation. Okay. So what are the objectives of this lecture? So we are going to do two things at the end of the lecture. One is to perform stress transformations from one coordinate system to another in 2 dimensions. And the second thing that we will learn in this lecture is how to compute or calculate principal stresses and principal directions using these stress transformation equations. Okay. So what are we interested in? So we have a stress at a point here indicated by this square. So essentially the point is P, and based on this xy coordinate system, we essentially have a sigma x, a sigma y, and a tau xy. What we are interested is essentially trying to find the stresses at the same point but in a different coordinate system. So now we start with this xy coordinate system and we are trying to get the stresses at the exact same point in the x prime, y prime coordinate system. So that is what we are interested in. Okay? So how do we go about doing that? To do that, what essentially we do is we take the square, okay, and then we make a cut along this particular direction, which means that the normal to this plane here is along the x prime direction. Okay, so the new coordinate system x prime, y prime, one of those directions is perpendicular to the wedge here. Okay, so once we do that, essentially we separate the wedge out and look at the free body diagram for that wedge, and that is what we are going to do next. Okay, so now if I take this wedge out from the square, then I have sigma x acting on one face, sigma y acting on the other face, and I still have this tau xy acting on these two faces. However, on this inclined face, okay, I have different stresses. So the normal stress on this inclined face is sigma x prime, and the shear stress on this inclined face is tau x prime y prime. Okay, what we are interested is trying to find out the sigma x prime and tau x prime y prime in terms of sigma x, sigma y, and tau xy. So how do we go about doing that? So for doing that, we essentially look at the force equilibrium for this wedge in the x prime and y prime direction. So just to remind you, this is the x prime direction and that is the y prime direction. Okay, so that is what we are going to do. So before we consider the force equilibrium, we essentially first have to figure out what are the areas of the faces of this wedge. Okay, so how do you go about doing that? Okay, so what we say is that the area of this diagonal face, we assume that it is going to be delta A. Okay, if the area of the diagonal face is delta A, what are going to be the areas of the vertical and the horizontal faces? Okay, this comes from just simple geometry. So if this area is delta A, then the area of this face, at the bottom is going to be delta A times sine theta, where theta is the angle between the x prime axis and the old x axis. So that is something that you must keep in mind. The theta is always defined as the angle between x prime and x. Okay, so if this area is delta A sine theta, the area of this vertical face is going to be delta A cosine theta. This just comes from plain geometry. Okay, one thing that I want you to keep in mind is that when I talk about this wedge, I assume that the wedge has a depth of delta z in the z direction. Okay, but this is just a 2D projection. Okay, okay. Now we know what the areas of the different faces of the wedge are, and what we are going to do is to calculate the forces on the different faces of the wedge and use those forces to compute the force equilibrium. Okay, so let's go about doing that. So again, I have the wedge picture here. So this is the inclined face with delta A. The other two faces have delta A cosine theta and delta A sine theta as the areas. Okay, so now what I'm going to do is I'm going to look at the equilibrium of forces on this wedge for the x prime direction, which is this direction here. Okay, that is the x prime direction. Okay, so what I'm going to say is that because this wedge is in equilibrium, the sum of all forces in the x prime direction should essentially be equal to 0. Okay, so if I use that equation, what are the different terms that are actually going to contribute to force in the x prime direction? Okay, so let's start with the simplest one. Okay, this sigma x prime stress is acting on this plane, and the plane has an area delta A. Okay, and the force due to the sigma x prime in the x prime direction is going to be nothing but sigma x prime times delta A. So that is the first term here. Okay, that is the simplest term. It's very easy to figure out. It's just the stress multiplied by the area over which it is acting. Okay, that is the first term. Okay, now we have to figure out what are the other forces in the x prime direction. Okay, so that needs a little bit more clarity, and what we are going to do is we are going to look at one step by one step, one stress at a time. Okay, so let's say we look at this stress sigma x here. Okay, this sigma x essentially is acting on an area that is delta A cosine theta. So the force due to this sigma x is going to be sigma x times delta A cosine theta. Okay, so that is the term here. Okay, now this force is acting in the x direction, not in the x prime direction. So what we have to do is we have to find out what is the component of this force along the x prime direction. So if you do the geometry, then this force sigma x times delta A cosine theta, if you look at the contribution of that force along the x prime direction, it essentially has a cosine theta term. Okay, so sigma x times delta A times cosine theta times this cosine theta, which is essentially the component of that force along the x prime direction, that is the total force in the x prime direction due to this sigma x. Okay, so that is one term. Okay, but now we have several other terms that also could contribute to force in the x prime direction. Okay, so now let's look at sigma y now. Okay, sigma y is acting on an area delta A sine theta. So that is what we have here, sigma y times delta A sine theta. Okay, now again that force is in the y direction, so we have to find out what is the component of that force along the x prime direction, and the component of that force along the x prime direction is sine theta. So you have sigma y times delta A times sine theta times sine theta. Okay, so that is the second term, and remember both these forces are in the minus x prime direction, and that is the reason why you have a negative symbol in front of them. Okay, so that is the contribution of sigma x and sigma y. Apart from sigma x and sigma y, you also have a contribution due to this shear stresses that acts on this plane as well as this plane. Both the shear stresses are of course the same. They are both tau xy, but they can have different components. So if you look at this tau xy here, that is acting on the horizontal plane, so that has a stress tau xy multiplied by the area, which is delta A sine theta. Okay, and then if you look at what is the component of this particular force along the x prime direction, that actually has a cosine theta term. So it's going to be minus tau xy times delta A sine theta times cosine theta. So that is the contribution due to this tau xy here. Okay, similarly this tau xy here also has a contribution along the x prime direction. Again, it is negative, so that's why you have the minus symbol in front of it. So that is going to be tau xy times delta A times cosine theta, and the component along the x prime direction is sine theta. Okay, so we have now looked at the contributions of all the stresses along the x prime direction. Note that we didn't think about, or we didn't talk about the tau x prime y prime stress here, because it is normal to the x prime direction. So it doesn't have a component along the x prime direction. Okay, so we don't have to worry about that. So if you look at this equation now, what I can do is I can take all these terms here to the right hand side and then simplify it. And if I do that, what I get is sigma x prime is sigma x times cosine square theta plus sigma y times sine square theta plus tau xy sine 2 theta. Okay, all that I have done here is that I have actually erased all the delta a's. So essentially I have cancelled off all the delta a's. So you have a relationship like this. Okay, and the reason that you get sine 2 theta is because sine 2 theta is 2 sine theta cosine theta, and if you look at here, these two terms are identical and they have a sine theta cosine theta. So if you add them twice, essentially it becomes sine 2 theta. Okay, that is how you get this equation. Okay. Okay. This is one way of writing this equation, but there is also a different way of writing this equation, which is actually much more convenient to deal with later on. So you can take this equation here for sigma x prime and recast it as sigma x prime as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times cosine 2 theta plus tau xy sine 2 theta. And this is just pure geometry relationship or trigonometric relationship. Okay. Now, what you have done now is find out sigma x prime in terms of sigma x, sigma y, and tau xy, which are the known quantities. Okay. Now, what you can do is we can do the same thing for y direction or y prime direction. So we can look at the force equilibrium along the y prime direction. And if you do that, so you will again have different contributions. So the first thing to contribute will be the tau x prime y prime term here. That acts over delta A, so that is the first term. Then you have contributions due to tau xy and this tau xy, and then you also have contribution due to sigma y and sigma x. Okay, you're using the exact same procedure. You essentially find out what is the force due to each stress. So for that, you multiply the force by the area over which it is acting, and then you take the component along the y prime direction. And if you do that, you essentially get a relationship for tau x prime y prime that turns out to be something like this. It is minus of sigma x minus sigma y by 2 sine 2 theta plus tau xy cosine 2 theta. Okay, so what we have done here is we have written the unknown stresses sigma x prime and tau x prime y prime in terms of sigma x, sigma y, and tau xy, which are the known stresses in the initial coordinate system. Okay. Okay. Now let's go a little bit more further. Okay. We can actually do something similar to calculate sigma y prime. And if you do that, you essentially will get an expression for sigma y prime as sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 times sine 2 theta or cosine 2 theta minus tau xy sine 2 theta. Okay. So what we have done is these equations 1, 2, and 3 essentially specify the stresses in the new coordinate system sigma x prime, sigma y prime, and tau x prime y prime in terms of the initial coordinate system and the stresses in the initial coordinate system. Okay, so these three equations 1, 2, and 3 are what are called as stress transformation equations in 2 dimensions. Okay, now we can go a little bit more further and look at what is the direction along which this sigma x prime is going to be maximized. Okay, for that all we need to do is essentially take the expression for sigma prime and take its derivative with respect to theta and equate it to 0. Okay, if d sigma x prime by d theta is equal to 0, it means that sigma x prime is either going to be maximum or minimum. Okay, and that is something that you can figure out by taking out the second derivative. Now, if you do that, if you take the expression for sigma x prime, which is equation number 1, and take the derivative, you end up with an equation like this, which is minus sigma x minus of sigma x minus sigma y by 2 times sine 2 theta times tau plus tau xy times cosine 2 theta times 2 is equal to 0. Okay, so that is the expression that makes d sigma x prime by d theta to be equal to 0. Now, if you look at this equation number 4 and equation number 2, which is the expression for tau x prime y prime, what you see is that the left hand side of equation number 4 and the right hand side of equation number 2 are exactly identical. So what you have as the left hand side of equation number 4 is essentially the expression for tau x prime y prime. So this is something that is very interesting. What does it say is that when sigma x prime is either maximum or minimum, that essentially means that tau x prime y prime is equal to 0. Okay, so what is the physical significance of it? When the normal stress on a plane is maximum or minimum, then the shear stress is going to be equal to 0. Okay, and these planes have a special name called principal planes, and that is what we'll look at next. Okay, so if you look at a formal definition, then the planes on which the maximum or minimum normal stress occurs basically have 0 shear stress, and these planes are what are called as principal planes. And the directions corresponding to these principal planes are what are called as the principal directions. Okay, so just to give you an overview of what is happening here is that we started with this stress state, okay, in the xy coordinate system. You essentially have sigma x, sigma y, and tau xy. Okay. Now, if you rotate this particular cube or square by a specific angle, theta p1, which we'll come to next, what happens is that you essentially get a different square, and on this square, you essentially have a principal stress on one plane and another principal stress on the other plane, sigma p1 and sigma p2. And on those planes, you basically have zero shear stress. Okay? So sigma p1 and sigma p2 are the principal stresses, and on those principal planes, you have zero shear stress. And there is an obvious relationship between theta p1 and theta p2, which is that theta p2 is theta p1 plus 90. So essentially what you're doing is that, okay, you have a square, you rotate it by theta p1, and then the stress on that plane corresponding to the rotation of theta p1 is the principal stress number 1, which is sigma p1, and the stress on the adjacent face is going to be sigma p2, which is principal stress number 2. Okay. Now, this is the cartoon picture of how do you get sigma p1, sigma p2, and theta p1 and theta p2. But if you want to be more specific and to figure out which one is going to be theta p1, which one is going to be theta p2, there's a particular way to do it. So what we do is, you look at this equation here, equation number 4, which essentially tells you the condition for which your sigma x prime is going to be maximum or minimum. You take that equation and solve it. And if you solve it, you essentially get tan 2 theta should be equal to 2 tau xy by sigma x minus sigma y. So if you recast it, theta p, I have put it as theta pa for a particular reason, I'll come to it next. Theta pa is basically just half tan inverse of 2 tau xy by sigma x minus sigma y. Okay, so this is one of the solutions for the principal direction. Okay, we still don't know whether this particular theta corresponds to sigma p1 or sigma p2. Okay, and the way we classify the principal stresses is that sigma p1 is always higher than sigma p2. Okay, so for example, if sigma p1 is, if you have two principal stresses, 10 and 20, sigma p1 will be 20 and sigma p2 will be 10. On the other hand, say you have two principal stresses of say 5 MPa and minus 20 MPa, sigma p1 will be 5 and sigma p2 will be minus 20. So sigma p1 is always numerically larger than sigma p2. Okay, and now how are you going to find out what is the angle that is, or theta p that corresponds to theta sigma p1 and sigma p2? The simple way to do it, what you do is you found this expression for theta pa. Okay, I have written this as theta pa because we still don't know whether it's sigma corresponding to sigma p1 or sigma p2. Okay, you take this theta pa and then substitute into equation 1, which is basically your expression for sigma x prime. Okay, so you do that, okay, and then find out what sigma x prime corresponds to this particular theta pa is, which I have denoted by sigma x prime a. Okay, if the sigma x prime a is greater than both sigma x and sigma y, then this theta pa corresponds to theta p1. On the other hand, if sigma x prime is actually lower than sigma x and sigma y, then this theta pa that we calculate is actually corresponding to theta p2. Okay, so essentially you find out what theta pa is, substitute in the equation for sigma x prime, and see whether it is greater than sigma x and sigma y. If it is greater than both of them, then theta pa is equal to theta p1, and the value of sigma x prime that you get for theta pa is essentially your sigma p1. Okay, and the value that you get for theta p2, which is going to be nothing but theta p1 plus 90, that is going to be your sigma p2. And that is how you get the two principal stresses, sigma p1 and sigma p2, and the two principal directions, sigma theta p1 and theta p2. Okay, and I'll see you next time. Thank you.